Hello everyone, let's start. I'll share my screen. Okay. I hope you guys can see my screen.
Yes, we can.
Okay, thank you. Okay. So this lecture was kind of a short one. It's a practicum of transformers, and he also goes into a little bit of depth into the attention. So attention is the main, as you all know, attention is the main feature of transformers. There is no recurrence or convolution. It's the main concept of This is the main underlying concept of transformers. And yeah, we'll be looking at it into a bit of with a bit of depth. So there are a few types of attention, and there are two bases of classifying them. So one is self or cross. Self is when you're attending with yourself, and cross is when you're attending to another set. Yeah, we'll be covering this with more depth. There's hard and soft as well. So one interesting thing that he says is attention deals with sets. So yeah, it's not sequences, it's sets. So that's something interesting that he pointed out. And So yeah, let's look at what self attention is. Suppose you have a bunch of x's, a bunch of inputs. So this could be words, right? So you have, say, t words, and these are, and as I've mentioned before, this is a set. There is no sequence under consideration. It's just a set of elements, and these could be words, right? So imagine t words, and so each word could be a vector of, so each of these element could be a vector of size n. So what you have is a huge matrix of size n cross t. So you have t words, and each word is an embedding of size n. You can think of it like that. So this huge matrix is of size n cross t, and like I said, each element in this set is belongs to Rn. So it's a vector of size of dimension n. And so what you are trying to do in self attention is you are trying to create a new representation for the input. You're basically trying to create some kind of encoding, right? And so this, you can refer to it as a hidden state, since it's the next state after the input state. And so in attention, the way you get this hidden state in, specifically in self attention, it's just a weighted average of all the other inputs, right? And so it looks something like this. So for a given x, say xn, okay, some particular x, x2 or x1, for anything, the hidden state of that would be a weighted average of all the other x's. So alpha 1 is the weight for x1, alpha 2 is the weight for x2, and so on. So this can be shortened as x, which is the huge x matrix that we saw here, that we see here, times a. A is a vector of all the weights or all the scores. So these alphas can be considered as scores. Yeah. So suppose you are trying to find the hidden representation of the first word, say x1. The way you do that is you take a score of all the vectors.
Alpha, I think so, is one hot vector representation. E, if I'm not, uh,
I think that is when you have hard attention, right?
yep,
So
okay.
hard attention is when you can attend to only one of the other words, one of the other elements. Soft attention is when you have probability scores
Hmm.
that add up to 1. Yeah.
Yep.
um yeah, suppose you have a word, suppose you're trying to find hidden representation of x1. So there will be a score associated for each of the t elements in this x. So you have alpha 1 x1, so there is a score associated with x1 itself. So alpha 1 x1, alpha 2 x2, alpha 3 x3, and so on. And that is how you get the hidden representation of the first element, and this thing is repeated throughout. And yeah, you basically get the new representation for your input. And like Mayank said, in the case of hard attention, one of these alphas will be 1 and the rest will be 0. In the soft attention, you are having probability scores which add up to 1. Okay. Yeah, all the scores have to be greater than 0. And how do you find these scores? So that's what they have given here. Um, so this consider a particular x. It could be x1 or x2. For a particular x, the way you find score is you take a dot product of that x with every other x. So x1 with x1 dot product with x1, x1 dot product with x2 will give you the scores, and so on will give you the score of each of the element with the particular element under consideration. And you write it in shorthand with this matrix. I mean, yeah, you can do it the whole thing together with this matrix multiplication, right? So you take the transpose of x and you multiply it with the particular x under consideration. So what happens in matrix multiplication is just scalar products, right? And scalar product of the first row with this x, the second row with the x, third row with x. I mean, yeah. And what you get at the end is a vector of size t. Because you have t elements in x, you have a score for each of these elements. Yeah. So that's how you end up with a vector of scores, uh, which represents the attention, right? How much attention, um, or how relevant it is. And yeah, so those are your weights now. Um, so let me try and understand this. Xi. Yeah, so for each of these x's, you have a score vector which will be of the same size. So for x1, you have a scores or a weights vector. For x2, you have another, because you have to find hidden representation for each of these elements. So each element will have its own uh, weights vector or scores vector, whatever you want to call it. And so that implies there is a big matrix of A's, which is capital A. So this capital A matrix contains the scores of all of the elements. So it's of size t cross t. So for each element in X, you have the scores corresponding to each element, if that makes sense. So that's why it's of size t cross t. I hope this made sense. You can ask any questions if you have. Okay. So um, so what you get from these scores is you get a hidden state for each of the elements, right? And how do you get that? That's what we have seen here. It's the hidden state of x1 is the weighted average of over all the inputs, and the weights being the alpha or the a that you just saw, the a vector. And then if you put them all together, you get the combined hidden states, and which obviously has to be the same size as your original x. So you have your x, and then you do self attention on top of it, and you get the next layer, which has to be the same size, n cross t. And how, and yeah, in shorthand you do it like this. I mean, in matrix format, I mean matrix representation, you can do the whole thing in a single step. So you have that huge x matrix, and you multiply it with the a matrix, which are the weights or the scores that we just saw. Yeah, so this in a way represents the entire thing that we have been looking up till now. um okay, so now he talks about like an analogy for what attention is doing. um so key value store, it's a paradigm for storing, saving, retrieving, querying, managing an associative array dictionary hash table. So so the example he gives here is so the example he gives here is, I think, video retrieval. So suppose you have, I mean, this similar to what YouTube or any video site or anything does, right? Suppose you have a bunch of videos, and um, the title of these videos can be considered as the key, and the value is the actual content, which is the actual video or whatever recipe or something. um, yeah, whatever recipe document, which is the actual content of the thing. And then you and then you have a query for which is the thing that you're searching for. Suppose I mean, taking the same example that he gives, suppose you have a huge recipe website, and you have recipes of a bunch of stuff, and the key would be the actual name of the food, and the value is the actual recipe. And then you search for something like pizza recipe, and then that would be the query, and then you do a similarity matching of this query with each of the keys, and the one that which gets the highest score, you retrieve the value of that. Or if it's a soft argmax, you kind of take a weighted average, and you take out the values of those things, the top, whatever. Yeah, you take a weighted average of the values. So this is like a way of understanding what attention is trying to do. Yeah. So you, so to do this kind of attention, you basically take projections of the input matrix. So you have a query vector, key vector, and a value vector, which are all yeah, he says rotations. So they are all rotations of the X matrix. Yeah, so these are just different projections of the X matrix, and these help us do attention in I mean, in this particular type of way. So the reason why, I mean, the reason why you can't just do a I mean, dot product of the X itself is there is no learning here, right? You can't just do dot product of X and then see which is the most similar one. You can't do any machine learning there, and you have to let the machine itself learn how to do attention. So that is why we create so these WQ, WK, and WV are learnable parameters. So in a way, you let the system learn um, which are the most important words to my query and things like that. Um, yeah. So you have, so from each of the x's, so x, this particular x could be the embedding of a word, right? And you create a query vector out of that, you create a key vector out of that, and you create a value vector out of that. So all words have their own query, key, and value. And so suppose you have a particular word and you want to find the hidden representation of that word. So you take the query of that word, and then you find the score of that query with all the keys of all the other words, right? And then you get a score out of that. So the dot product of query and key is like a proxy for the score or the relevance. And then you take a weighted average of the values of um, of all the words to get the new representation for the current word. So this particular thing is like an analogy for that. Yeah.
Yep. Just to add, the difference between Q and K is just um, a, a simple representation of the vector in which it is turned. I mean, matrix is multiplied with the key vector, and it's a bit different, but uh, 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 so it represents uh, how do I say it? Kind of a vector which takes which when dot protected with the weighted matrix has a different representation as compared to the Q. Am I correct in the assumption here, or?
Yeah, I think so. Yeah. I mean, the basic difference is yeah, the matrices that you multiply to get those query and key are different, right?
Mm-hmm. Yeah, cool. Thanks.
um okay. Something that we have to take care of at this point is the query and key have to have the same dimension, because only then you can um I mean get a similarity score between the query and key, right? If they are of different dimensions, you can't compare them in any way, but the value is allowed to have a different dimension. So taking the analogy here, to compare your query of uh, to compare your query and key of whatever recipe you're searching for, they need to be the same dimension, but the actual recipe can be uh, like multiple, like a long, it could be multiple pages, so its representation can be arbitrarily long. It's not relevant. um,
There
so I
is
think here,
there is something, I don't know if it's relevant, but there is a concept of dequantization, right? So if if you see Q equals WQ times X and K equals WK times X, right? And these two are random matrices. So I wonder, because you cannot compare an X and X directly, if you send them to these random matrices, you somehow fuzzify these two vectors, and that allows you to, kind of learn the distances between the two, right? So this is the dequantization stuff I learned in the unsupervised study group. So I was thinking whether there is a connection. Maybe there is, maybe there is not. Just wanted to mention it in case somebody else
Why
has
is
idea.
it called dequantization?
So essentially you are, so let's say you have, well, dequantization in this sense is that if you have categorical variables, um, they occupy a particular point in space, right? So instead of that, you are trying to fuzzify them and, perturb them. So you basically, instead of returning X, you return X plus or minus um, some random variable within that range. So, and that makes learning easier, less peaky, right? So I don't know, maybe, I just thought that I kind of made a connection from a dequantization and this while you were talking. So
Okay.
not sure if this actually means anything, but yes.
Okay. So to me, I kind of prefer to understand this from a linguistic sense, right? I mean, that to me makes more intuition, even though I have not understood completely. So I think this was mentioned in the uh, previous video. So so query could be some. So suppose you are having a word. Um, um, I mean, I can't think of something right now. So suppose you are having a particular word, and uh, the query could be something like, suppose given, assume the given word is a noun, okay, and then there is a pronoun which refers to this noun a few
Right,
words
right.
ago.
Mm-hmm.
So the query could be query could be like, give me the pronoun. I mean, this is all somehow done in vector space, right? Query could be something like, show me the pronoun that refers to this noun, and then the key could be something like uh, which says I am a pronoun, right? So the query is asking for a pronoun, and the relevant key would be saying I am a pronoun. So the Q and K, in that case, the score will be high, and if it's not a pronoun, the scores will be low.
Yes, yeah.
And then you retrieve the particular relevant word, which is the actual pronoun for this particular noun. And yeah, I mean, to me, thinking in that sense slightly makes more sense.
Right.
But yeah, this, I mean, yeah, thinking the linguistics terms gives more intuition for me. But yeah, I mean, something else might be happening in the case where we are not talking about text.
Right, yeah.
Yep, I think so. There are two aspects to it. One is with respect to the vectors. If we quantize vectors, then we try to truncate it, and what will be the representation for example, if we had originally 32 bits of information, and we quantize it to 8 bits, then what will that represent in the manifold, or how will that actually map to it, versus there is some other quantization theory which totally deals with uh, uh, the statistical significance of how the quantization that is in the traditional sense that we do, like if we have our model and we are trying to quantize it to run it on uh, mm, constrained devices, then what will that represent? So yeah, uh, I think we are, if we hit on the first part of the quantization factor with respect to the vectors that we talked about, then yeah, those densities and I think so. There is a recent research too with respect to the quantization in the text of, and how do the kind of like uh, I'm not currently fully familiar with it as uh, Sujit talked about, but yeah, I think if I find something, I will share it in the chat. Thanks.
Okay, thanks, Mike. Um, okay. So one thing we can agree on is you can't do self attention without having these query key and value concepts. It's what allows the model to learn which word to attend to and all of that things. You can't achieve something like this obviously with this kind of dot product attention. So that is why we have this query key and value to enable that kind of attention to be learned. And yeah. Okay. um okay, so from each x you calculate query key and value, which are all uh, I mean, query and key have to be the same dimension. V can be of different dimension. And when you put them all together, you have a big Q matrix, K matrix, and V matrix. Just we are just putting all the queries together and keys together and so on. Um, so here we are assuming all of them are the same dimension D. So all of these three will have the dimension D cross D, since you have T elements or T words in your sentence, and each is of dimension D. Um, so here, as I mentioned, you take the dot product of query with each of the keys. So you take a particular q and then you matrix multiply it with the key matrix to get scores for all the x's. And since you have t elements, you have t such scores, and then define the hidden state by taking the weighted average of the values. So v times a. So this is now the new representation of your word. And then yeah, you can, in matrix representation, the whole hidden state calculation can be written in this way. H is equal to dot product of the value matrix with capital A. So capital A is the score for scores for all the elements in X. I mean, this is similar to what we saw earlier. So I hope this makes sense. So these scores are obviously calculated with the dot product of, I mean, with the dot product of keys with each of the queries. I hope this was not confusing. Um, moving on. Um, uh, yeah, so this, I mean, these are just implementation shortcuts, I think. So you can do all of this in a single step. You can just stack all the weight matrix, the K matrix and the V matrix, and then if you multiply it with the given X, you get a stacked Q, K, and V, which would be obviously of length 3D, since each of these is of length D. And then you can have parallel attentions, which is what head means. So considering H parallel attentions or H heads, we get a vector which is of length R3HD. Yeah, so 3D into H for each of the heads. So when you have parallel heads, you have a separate WQ for each of the heads, a separate WK for each of the heads, a separate WV for each of the heads, and yeah, all of them are just stacked and multiplied with X to get the stacked queries. And yeah, we talked about this last time. So separate heads um, are useful for getting different types of attention. And the example I think is mentioned in the blog post, which Alfredo also had mentioned. um I don't know if I can find it now.
Yeah, I think that's the one.
Is it here? Yeah, I mean, you can read this. It's the reason why, I mean, they're just talking about why you need multi-headed attention. It expands the model's ability to focus on different positions. So if you have just single attention, you are just allowing it one particular way of attending to the words. Multi-headed attention, it can attend on multiple things.
It's similar to filters in CNN, right? So you basically want to convolve it using multiple filters because you want to see different aspects of the image,
Mhm.
right?
Yep, that makes sense. Yeah. Yeah, I mean, sometimes you want the pronoun of this word, sometimes you want the adjective of this word, so both words are relevant to the particular word. So in that case you would need multiple attentions to learn something like that. Okay. um so transformer architecture is, it has an encoder and a decoder architecture. So this is for neural machine translation or for something like summarization. Any text to text or sequence to sequence would have an encoder decoder architecture. So this is similar to the auto encoder that we have seen. So there is an encoder and decoder architecture. So what does the encoder have? So um, the encoder in simple terms is just, you are just trying to get um, good representations of your input. um, uh, yeah, which can be, yeah, you are just trying to find some good encodings or representations for your input. And so you have your excise, which are the words or any inputs at the bottom of the encoder. And then the first part is the self attention, which we have just seen. um, so self attention gives you the hidden states with the same steps that we have seen. It has query key and value for each of these x's, and then you get the hidden state out of that. And then there is an add norm layer, which is layer norm. So layer norm is, it's just a different type of normalization. um, so batch normalization, you do normalization across the batch. In layer norm, you do it across the layer. And then there is a residual connection here, which is, I think we talked about these in the last lecture, um, which allows the gradients to flow easily. It is similar to the residual block in ResNets. um, I think we should go to the code, maybe that will help us understand this better. um, yeah, there is a one uh, single layer, I mean, there's a one convolution that comes after that, and then followed by add and norm, similar to this one. Okay, we can, okay.
Yep, and there is a cross attention too,
Yeah,
which is a, yeah.
so cross attention comes in the decoder. So this is the only difference, I mean not the only difference, but this is the difference of the transformer decoder and the transformer encoder. So in transformer decoder, in between these two, you have a cross attention and add norm here. So the simple way to describe this, the reason for this is, suppose you're doing some kind of translation from English to French or something like that. um, so your decoder is actually something that generates text, right? So in this case, your decoder is something that generates French sentences if you're translating from English to French. So in that case, if your decoder was all by itself, it would be just a normal language model which takes a start token, generates the first French word, then feeds it back in, then attends to itself, then generates the second word, feeds it back in, attends to itself, generates a third word, and so on. But now, what we are trying to do is, we are trying to create something which translates English to French sentences. So in that case, um, first you do a self attention, um, which creates the hidden state from the input, and then you want to attend to the output of the encoder. So your encoder takes in English words, and then it creates hidden states or hidden representations or encodings for those English words. And then, so when you're trying to generate a particular French word, what would help is if you are able to attend uh, to the particular English word from the encoder output, right? Because you are not just trying to create a random French language generator, you are trying to create something that translates from the English word. So that is what this cross attention helps in. So you take the query from the output of the self attention, and then your keys and values are created from the output of the hidden state of the encoder. So uh, so to repeat again, the query is from the output that comes from the self attention, and keys and values are from the output of the encoder. And then you take the q and you multiply it with the same thing, you multiply it with the k of all the uh, all the words from the encoder output. And then the hope is that you, suppose you're trying to translate the French, suppose you're trying to generate the French word for home, and then you want to attend to the English word home in that case, so that you actually generate the correct word. I mean, yeah, something interesting that one of the students asked this in the lecture. So what do you get when you do cross attention? The thing that you get is, you get a weighted average of the English word, right? So suppose you're trying to generate the French word for home. Once you do a cross attention, you get the value of the English word home. So how do you generate uh, a French word from that particular English word? So the answer that Alfredo gave was that, I mean, it's kind of language agnostic. So in those higher layers of the encoder, it has actually learned linguistic concepts and meanings. So yeah, that was the answer that he gave in the lecture. um are there any questions or anything to add? I think it was kind of difficult to just understand it from this diagram.
Yeah, I'm a bit lost about this diagram. In first place, what would be YHat, the set of YHats in this case?
Okay. Maybe I'll try to get a better the classic transformer diagram is actually better than this, I believe.
YHat is the output of the encoder, right? So the not the hidden part, the output at that position.
Okay. So YHat YHat Sujit, could you repeat what you just said?
I said that YHat is the output of the encoder. So if you go up to the previous slide, so this returns just H, but sorry. YHat is the output of the previous time step of the decoder. Sorry.
Yeah, so that is when during inference time, right? So in normal training time, YHat is, suppose you're translating English to French. So in the encoder, what you're giving is English words. Suppose you have a sentence that you want translated, the whole sentence tokenized obviously is what you feed into the encoder, and what you get out of the encoder is good contextualized representations of the English sentence, and what you feed into the decoder is the French words,
Yeah, the label
the
that you already
corresponding,
have.
yeah, the corresponding French translation of that English word. And the first step is the same. You do attention to get a contextualized representation. The only thing that you have to take care here is there is a mask here. So suppose you're trying to generate a particular French word. I mean, so the thing is, when you're translating, you are not allowed to look at the future, right? It's just cheating. So you are only allowed to attend to the previous words. Okay. So first you create a representation with just normal self-attention. And if you were to just continue and generate a French word, so that is a normal language model, right? You are just generating random French words by just looking at what previous French words have been said. Uh, it's a normal language model, but here you want to translate English to French, right? So this is a conditional language model. So in that case, you also have another attention, which is cross attention, and where you attend to the words from the output of the encoder. So these are the hidden representation of the English sentence. Suppose you're trying to generate, like I said previously, you're trying to generate a particular French word. Um, it helps to attend to the corresponding English word from the output, and yeah, that, and then yeah, you have come. I mean, once that attention take place, you come up with a even better representation, and then that helps in uh, predicting the correct French word. Did that make sense at all?
I think so.
Yeah, I think it makes sense.
So so you can, I mean, maybe this would help. Like the normal GPT model, the GPT-3 or whatever, it's just a simple decoder where you are just having I mean, this is just an example, it won't help much, but just for information, like the normal GPT model is a simple decoder where you are just uh, having, you are just generating, it's a normal language model, right? You are just generating French words You can just give a bunch of English words and it will generate a nice sounding paragraph from those 2 3 words. And then for example, and then something like BERT is just an encoder. It's just a transformer encoder. So GPT is just the decoder and BERT is just the encoder. So what does BERT do? You give it a sentence and then it gives you good encodings for that sentence, which you can use in some downstream task, right? And you combine those two together, you have the complete transformer architecture, which you can use for translation, summarization, and things like that. Yeah, this is just extra information. Is there anything else?
Yep. Here we can see that in the transformers encoder. Let me try to annotate. Uh, right.
Yeah, I
If
think
you
this is actually a better diagram. Yeah, Mike. Yeah.
yeah, if you go back to the slides there, as Alfredo showed, yeah, here I think so. We have a HI. Let me try to clear it up.
Do you want to share?
No, no, no.
Okay.
Please just freeze the screen for a bit. I will annotate
Okay.
here.
Yeah.
Yeah. Here we can have h of I. So that can make sense. Uh, these h of i's that are coming in. So from this, in a sense that those uh, uh, parameters that he has represented, it's kind of like this uh, computes on this too. So here we have this kind of a HFI that is being outputted, or you can say this parameter. If we try to conceptualize the diagrammatic representation of how Alfredo wanted his thoughts to be conveyed. I think so. It is around 47th minute in the video that he had. So yeah, that was. If you guys understood what I was trying to communicate here with respect to the from ith I 1 to t. So that were the time steps, and this one convolution block that kind of like channelized our uh, how do I say it? The right word. It was like try to get it like a convolutional sub block that had some sort of a bottleneck representation. So here that uh, uh, reduction in the compute is going on the one convolution block, and then the addition and the layer norm that that we had. So that's the repetitive block that is being done after this HI step that I just did. So yeah.
Okay. Yeah. So you can have multiple encoders, multiple encoder layers, which are stacked on top of each other, and similarly, you can have multiple decoder layers, and yeah. So one thing I didn't say is during inference time, the yi is the previous word generated by your decoder. So you do I think it's called teacher forcing, right?
Yes.
So you just feed whatever word was generated previously, that becomes your input, And yeah.
Teacher forcing is basically sending the next label word, right? So regardless of what you generated during training, you basically send in the next word. So that is essentially you are the teacher, the label is the teacher, and you're forcing the student to learn what you wanted to learn. Right, so that's
Okay. So teacher forcing is during training. Okay, I got it wrong. Teacher forcing is during training, right?
yes.
Okay, so you actually feed the correct labels.
Right.
Okay. And during inference, you feed the
Generated, the
output that you
predicted,
generate.
right.
Okay. Okay. If there is nothing else to add, we'll go to the code. Does anyone have anything, any other points or anything that I forgot? I mean, I'm sure I didn't do a great job, but still.
It was fine.
Yeah, I thought it was good.
So, I actually couldn't. I was not able to get the code running because I didn't try it early enough. So the torch text that he uses is now in a newer version, so it does not have these field and stuff. So I used to use torch text earlier, but now they got rid of this field thing because they wanted to make it compatible with PyTorch, so they got rid of that completely. And then I tried installing an older PyTorch, older torch text, and it just gave some completely weird error which I could not solve at all. I should have probably tried running this earlier, but anyway. Was anyone able to run the whole thing? I mean, it probably just works from top to bottom, but you just need to have the correct torch text version. Okay. So he just like implements all the things that we have discussed. So there's a class for multi-head attention. So it just takes the number of heads that you want. Uh, D underscore model and D underscore input. D underscore model, I think, is the dimension of your embedding. I'm not exactly sure of the difference between D underscore model and D underscore input. Does anyone know the difference between these two?
I think it's the internal model size. If you look at the self WQ, the weight matrices, they, that is the basically the embedding size.
Mm-hmm. The size of the embedding, yeah. Okay. Mike, do you want to annotate something?
Yeah, I was thinking D underscore model and D underscore input. I think so. D underscore input also refers to the self attention versus cross attention part.
Mm-hmm.
So
Oh,
if anything is given here, then it corresponds to the
cross.
yeah. So
Okay.
D underscore input
Right.
will refer
Yeah.
to, yeah.
It's up here.
Okay.
So
Okay, I didn't. Yeah.
there's another funny thing when in the def of the class, you see if D input is none. Oh, I
Yeah.
see. Okay, they just said dxq equal to dxk. It's just equal to's there, right? So they are
Yeah,
all
they're all
set.
equal. Yeah.
Okay, I see. And then the other else in the else is okay. Interesting.
Okay.
Why is that? I'm sorry. Maybe it's a basic question, but why the difference like that?
I think
Maybe more.
all they seem to be doing is if you don't give a dimension, then they set the dimensions.
Oh, okay. Oh, I see. I see. That's the
So
dimension.
if you don't give a dimension for the input embeddings, for examples, then they make it all be what the dimension of the model is.
Okay.
If you don't give D input, then it sets the various DXQ, XK, XV all to be D model. And if you give it, then it sets those pieces to whatever you give the embeddings to be.
So if you,
So
I
for
think
example, if you're using glove 300 or glove 100, then you would say, oh, I'm using an embedding of 100 or 300 for my glove vectors. Then it will set the internal XQ, XK, XV to 100. If you don't give anything, then it will use its own default, which is D model.
Okay, so if you don't give, I mean, the thing is, query key and value can have different dimensions than the dimension of your embedding. So if you don't give anything, it by default uses the dimension of the embedding. Otherwise, it uses what you have given.
Okay.
Is that right?
Yeah, that's what at least that code seems to be doing, right? If your input dimension D input, you don't specify it, then it makes whatever D model is, it uses that value. If on the other hand, you say my dimension of the input, which I assume is the embedding size for my input is something, then it uses that.
Okay.
Probably this is this is based on what Mayank said as well. So this is probably because if you don't specify D input, you are talking about self-attention, right? Whereas if you do specify, you are saying here is the dimension of my hidden vector, and this needs to be converted down to the model vector. Maybe.
But okay, yeah, that could be right.
Yeah, but also with respect to if we try to yep, the D input changes with respect to the self and the cross attention part, and I think so there was difference with when we take it down the line with respect to the different ways of those blocks that are being repeated. So if we apply that here, then the D input will obviously change it. The Q, the K, and the V, but and I think so. There was some other aspect to it that I'm currently missing. Maybe we can get to it later.
Okay. So you create WQ, WK, and WV are the matrices for generating the query key and value. So you initially generate them as random matrices, obviously, and so yeah. So the D underscore XQ is the dimension of the query, and this is, like we said, the embedding dimension, and the bias is false since you just want a normal matrix. Output of all sublays need to be of dimension the model. I think this is just a simple linear layer that we use later in the model. And then yeah, we also later on split into the number of heads that we have, and that requires that the dimension of the model be a multiple of the number of heads. And this is the implementation of the dot product attention. So it takes in the actual query key and values, and here it does the dot product between the query and key to get the scores, and then you do a softmax on the scores. So scores just gives you the actual dot products of the vectors. So it won't be it can be arbitrarily large or small, so you need to do a softmax on that, and then you take the weighted average of the values to get the hidden states, which are the output of the attention. And yeah, he has renamed nn.softmax as nn soft argmax, because what he says is this is the proper term for softmax, soft argmax. Okay. So this is the forward of this multi-head attention. So here he actually creates the query vector uh, by multiplying the xq. So xq is the it's the input for which we want the query to be made. This is the xk is the input from which the keys should be made. Xv is the input from which the values should be made. So these three will be equal when it's self attention. In case of cross attention, this will be the output that comes from the decoder self attention, and these two will be the outputs from the encoder. Yeah, so for self attention, all three of these will be the same. Yeah, so once you create the query vectors, you split them by the number of heads, which is what this function does, and then you create query key and value, and you get the hidden state by doing the scale dot product attention on these three. So like we've already seen, there's a dot product of q and v, and then using those scores, you take the weighted average of the values. So this gives you the hidden state. And these are split by heads. So you put them back together, which is what is done in this function. And then you have a final linear layer. Yeah, it's just a simple linear transformation from D model to D model. So this part is the multi-head attention. Here they just do a simple check. So they create, he creates a key tensor, a value tensor, and a query tensor. So for query, obviously you just need one vector, and he just tests the multi-head attention with these random tensors he created. Yeah, it just gives out some weights for each of these values, and the output tensor is obviously the weighted average of the values. Okay. 1D convolution with kernel size 1. So this confused me a bit, the reason why he calls it a 1D convolution, but then it made a little bit more sense to me later, but maybe I can explain it with some diagram here. So so the reason why it's called 1D convolution is there is a linear layer, and you apply that linear layer separately on each of the words. So this word thinking machines, right? It goes through the self-attention, add and normalize, and then you get the hidden representation for thinking, and you get the hidden representation for machines, right? Both are separate, and then you uh, pass them both through a linear layer separately. So this one goes through a particular linear layer. I mean, both are the same layers, but they are uh, they are fed. I mean, they are fed into that linear layer separately. So it's similar to the same kernel being applied to the first element and the second element, right? So that's why it's called as a 1D convolution. But the underlying thing that's happening is the hidden representation for the word thinking is fed into a linear layer, and the hidden representation for the word machines is fed into the same linear layer, but separately. So that's why it's he calls it as a 1D convolution. And yeah.
Yep. And trivia to add, there has been a lot of discussion on this on Twitter with respect to uh, is coordinates required in transformers, and whether MLPs are coordinates in fashion by Likun and others as well. So that's a trivia for you guys.
I
Ah,
saw
well,
there was a paper recently, right, which brought back MLPs for ImageNet, I think.
yep. There was they just trained it on that was a MLP mix. If I'm not wrong, uh, that was the paper in which they trained up on TPUs with respect to uh, 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 finding the ways of uh, yeah, on new MLP architecture for vision. That it was with respect to the channels and those feature spaces being concurrently mixed up. If you click on this, there's a very good diagram with respect to how they show the different representations of both of them. Uh, uh, with respect to those channels and with those rows and those. Yep, that's it. So they are trying to mix it up here, those channels and patches. So yeah, uh, and this performs kind of like good if we just have to scale it up. So this was with just uh, uh, trying on one thing and seeing if it works, and it does actually. So yeah.
Okay, interesting. Um, okay. So that's what happens in this 1D convolution. You are just taking the hidden representation of the word, passing it through a particular linear layer. So you are expanding from D model to a hidden dimension, and hidden dimension back to D model, and then a ReLU activation. I mean, you do this for the same purpose that you have a layer in neural network, right? You just want to uh, yeah, learn complex representations and so on. But yeah, that's the main purpose of this. But the point is, uh, it's just linear layers which are applied separately to each of the words. So it's similar to a kernel being applied across an image. So that's why he refers it to it as a 1D convolution. Okay. So now we have all the components for a transformer encoder. So if you look at the forward method, initially it takes in so this side yeah, for an encoder obviously you just have self attention, right? So it takes in the x and then you do self attention on itself, right? So you create the query key and value from the same input, and the output from the attention is you get the hidden state as the output from the multi-head attention, and then you do layer norm, and then this is the residual connection. So you add the original input with the attention input, and then you do the feed forward, which is this thing that we talked about, the CNN. And then there's one more of the layer norm and residual connection. So this is encoder layer. And you can have many of these encoder layers stacked on top of each other. For example, BERT has 6 encoder layers, 6, or the big one has 12. Okay. So there's and then there's something called positional encoding. So as we talked about it earlier, attention is acting on a set. It's not acting on a sequence. So attention is actually order invariant. So you can just shuffle the words and you would get the same type of attention output. So this is something that we obviously don't want when we are working with sentences and so on, because in sentences the order is crucial, it's important. So what we do in that case is we create a separate embedding or encoding called positional encoding, and you just add it along with the actual embedding of the word. So this is like a formula for the positional embedding. So I is the actual position, I or p, I'm not sure. So basically uh, you just get a particular value uh, that's unique to each position in the word. So it kind of represents the position of the word in the sentence, and you add it to the word embedding. So this is how you kind of tell the model where my word is in the sentence relative to other words. Yeah.
Is the 10,000 there referring to the size of the vocabulary?
I don't think so.
Thought, I thought something. Yeah, I thought something like that from the blog, but like here, if you see, yeah. So, oh, but he doesn't have the formula here. Yeah, here it's an example with 20 words, right? Like, so it's the sine and the cosine for 20 words, and each word is, and the vector is each 512. Um, okay, it's a minor. Okay, it doesn't matter. Yeah, it's okay. It's just a minor detail about, but it's a clever idea. I like to use the sine and the cosine. Yeah.
Yeah. I think we should. I'll just quickly check if I can find it in this, or I'll
Okay.
leave it.
Yep, it's the wavelength with respect to I think so what they have defined. Yep, yeah. Here in this paragraph, that's the geometric progression of the wavelength from 2 pi to 10k dot 2 pi.
Yeah, but why pick 10K, right? Like, uh, but it's
Uh,
okay.
yep. I think so that it might represent the best wavelength with respect to the positional dependency that it had to encode. So,
Okay.
yeah, because uh, they might have tried with the different parameters here, and
Okay. I see.
this, yeah,
I see. So
this
they
this
tried a
might not have.
bunch. bunch of numbers and then 10K was the best or something. Yeah. Okay.
Maybe they just chose a nice round number. I don't know.
Yeah. Yeah. Okay, thanks. Then we can move.
Okay. So, so like I said earlier, you have your word embeddings, your position embeddings, and what you do is you add both of them so that there is information about the position of the word, and then yeah, there is a layer norm at the end of that as well. So what this module gives you is it gives you the embeddings of the words which you feed into the encoder. And the thing to notice, the embeddings have information about the position as well. So this is the whole encoder. If you see the forward, you get the embedding, which is the which is the uh, which is the summation of position and word embedding and the layer norm, and then you feed it through n encoder layers. It yeah, you can have as many encoder layers as you wish stacked on top of each other, and then the output is that you get is the final encoder output. Yep. Yeah, so now he in this example, I guess they have not shown the whole transformer architecture with the decoder. It's just the encoder that he has shown here. So here he uses the IMDb dataset and uses purely transformer architecture to predict the I guess this is sentiment, positive or negative sentiments. So so it has two things. It has the encoder, which is the encoder that we have created here, and then at the end of the encoder, he has a dense layer fixed at the end, which predicts the positive or negative. So I guess this is the number of labels. Forward. Does anyone know what is torch.max? What does this do? So the confusion that I have here is the encoder output is D model times the number of words, right? So how do you how does it feed into this dense layer? So I guess torch.max is just takes a max of all the elements in the input tensor.
Can you check the definition about the dimension? So when it, because it says dimension equal to 1, and like, yeah, one thing
That's
I've
the
been,
axis, right? Yeah.
okay, yeah, like, I mean, which axis? Like, so,
So I think the output of the encoder will be of dimension D model times sequence length,
okay,
or is it? Yeah. So batch size. Okay, there is batch size as well. Batch size. This is the number of words in your review or whatever in the text. This is the embedding size D model, and then what he does here is he takes torch.max along the second axis.
okay, okay.
So which is this one.
Plus the,
So essentially what he's doing is he's just taking uh, the largest the largest of the for each of the 512, suppose your embedding dimension is 512. For each of the 512, he's taking the number from the word which has the largest value, and then he's creating a vector out of that. I don't know why he does this, but that's how he is doing it. Does that make sense?
Yeah, I think the process makes sense, but yeah, I had the same question like you, why he's doing that there. Um,
I mean, at the end of the day, he the encoder gives you an output of 512 for each of the words. So you
uh-huh.
have to uh, reduce that, or I mean condense that in some way to feed it into a another linear layer to predict the final output. And the thing that he chose is max. You could have easily done average or something else, I guess.
I see.
Yeah. Anyone else have any ideas or anything on this?
No, and then he's passing it on to the dense layer. So we have for that representation. So I think that will take the max feature that is required for the classification objective, and yeah, try to give that sort of a kind of like class that last to last layer. So in the end, I think so the last layer that he has used for the classification might be I think so that's the dense layer here, right?
Yeah. Yeah, it's a
Yeah,
simple dense layer. To,
yeah.
to
So I think so for the class labels that are being classified here, that should represent this, if I'm not
yeah, yeah,
mistaken.
that's just two, the positive and negative. That's all.
Yeah.
So I have one more basic question. So this class transformer classifier, can you, I was trying to relate like where it is in the PDF, but maybe PDF doesn't have it. So is it in the like the lecture notes, in the web page? Like, can you relate where this is to the notes?
It's not there. I
It's
don't
not
think it's
okay.
there in the PDF. Even in the actual lecture, he just talks about the few important things in this code, but he does not go through the whole code.
Oh, I see. Okay.
Yeah.
Okay.
Okay.
One thing we have done, so I find this is useful. So when you take sentence embeddings, and this is for search kind of purposes. So you take sentence embeddings, but you really want to search for paragraphs. So you would try to, max pool the sentences. So essentially your paragraph embedding contains all the best features for each of the embedding dimensions from all the sentences within it, right? So that's one reason for max pool, that you can use it for.
Okay, makes sense.
Also, the transformer classifier is something that you stick on top of the transformer, right? It's not part of the transformer architecture per se. It's just how do you use a transformer architecture to perform classification. So for example, even in BERT, you do whatever the BERT thing is, and then mask prediction, blah, blah, blah. And then you stick a transformer on top. That's the reason he doesn't get into much of the transformer classifier discussion, because it's almost like how do you apply transformer architecture to classification tasks, and you apply it by sticking a head on a transformer to do classification, and there's just one way to do it.
Yep. Yeah, and yeah, so BERT is something very similar to this, but so what BERT has, which this doesn't have, is BERT has a neat CLS token at the end. So CLS token is something that is already considered to represent the whole of the text. So you don't need to do any kind of max pool or average or anything like that. You can just take the output of the CLS token, which is a special token at the start of the BERT. So you can just directly use that for classification for something like this one. But here, since we don't have that, we have to do some kind of max pool. Yeah, yeah. And then once you do the max pool, you have your classic linear layer to just predict, where the output is the number of labels, which is 2 in this case for positive and negative. Okay. I don't think there's anything else of too much interest. After that, it's just the normal stuff. Optimizer. There's a training loop. Model.0 grad. Okay. Evaluation loop. Yep. Nothing much to discuss in specific. Is there any other question that anyone wants to discuss? Any other points?
Just a more like practical thing. So when you're going through code like this, how are you guys learning it? Are you doing like the Jeremy way and typing it everything on your own, or doing some other approach to get a good feel of the code?
I didn't do it here,
Okay.
but generally what I do is I put a lot of print statements in the code. I don't retype it, but I try to understand the code by looking at the vectors, looking at sizes of vectors and so on. So
Okay.
basically kind of debugging, stepping through it basically, but using print statements.
Okay, great. Thanks.
Yeah.
Okay.
And
I
he has
personally,
the sizes annotated in most cases. I think for me it is the getting the sizes correct and seeing what sizes and how the matrices multiply and yield the appropriate sizes is, I mean, here he has it annotated neatly, but that most other notebooks don't have it. So I annotate a heck of a lot around the sizes because that's what gives you the insight into how we get the result that you're heading towards.
Okay, thank you.
okay. I mean, I personally find typing the whole thing myself, it just helps in understanding it in a much better way. And yeah, usually I only look at code. I mean, it helps if there is a video explanation as well, but yeah, which is there in case of fast AI. But yeah, okay. Any other questions? So yeah, Sujit will take over now. He will discuss about the Albert, the Electra Bengali model. Yeah, thanks.
So this is basically a thing I kind of got an opportunity to do. So there was a thing on Twitter saying that people who spoke Bengali, they were inviting us to participate in a collaborative distributed training exercise to train a Bengali transformer model. So I joined up because, the other requisite was that you had to be able to run Colab. So since I spoke Bengali and was able to run Colab, I volunteered. Essentially, it's a distributed collaborative training. Objective was to pre-train the Albert model for the Bengali language. And this was a joint project from NeuroPark, Yandex Research, and Hugging Face. So NeuroPark is a group of, it's a nonprofit, and it's a group of, I think they're Bengali, mostly, scientists in India, NLP scientists, and probably all over the world by now. Yandex Research, of course, everybody knows the search engine, and Hugging Face, everybody knows, right? So basically, it's a joint project. NeuroPark supplied the idea for the Albert Bengali thing. Yandex Research supplied the training platform called HiveMind, which I will cover in a minute. And Hugging Face did. There was one person from Hugging Face. She did most of the programming to run this whole thing, including training the tokenizers and whatnot. So basically, so HiveMind. Let me share a link here So the platform for distributed training that was used was called HiveMind. And this is from Yandex Research. And basically, the idea is that each notebook user, like a Colab user like me, trains the model on a small portion of the data, right? And me as a notebook user is part of a peer group, and there can be multiple peer groups simultaneously training, right? And there is no, like a centralized point of control. So as I train, my results are shared with my peer group and averaged with my peer group, the parameters that I come up with, right? After every certain time interval. I share with my peer group, and the peer groups share with each other, again through model averaging, right? And periodically the current model parameters are dropped into a checkpoint. And so this is how basically it works. And it's kind of geared towards like people dropping off either inadvertently or by a choice. And if you drop off, your peer group basically the model average of your peer group gets destroyed, and your peer group members get redistributed into other peer groups, right? And their models, they acquired the model average from that peer group and continue on. So again, so no central coordination, and yeah. So this is basically what the HiveMind project is about. All of us use free GPUs from Colab and Kaggle. Kaggle gives you 30 hours of GPU time, by the way, per week. So I didn't know that. So that was something good to know. But I was actually interested, hoping that maybe we could use it in AWS, where I own all my properties, right? But as spot instances. So, if they go down, they should be resilient to that sort of thing. And it's not clear. I mean, they did mention that it is possible, but the instructions are not there yet. So maybe it will be there in the future. So yeah. So this is about here is the final product. So it's called Sahaj Bart. Sahaj means easy in Bengali and probably in many other Indian languages. So this is the model card that we our model is finally there. And if you go there and, okay, actually, let me share this. This is probably fun little thing to do. Desktop, share. So here's the model card. And this one says, Jiboner Shobche Mullaban Jinish Hoche, and masked, right? So it basically sees, what is the most important thing in life, right? And this is basically, okay. So the first one says Rupcharcha means like makeup. Shusastho is like health. Bhalabasha, love. Khabar, food, Bengalis, food, right? And chocolate for some reason. So any case, so there is a little thing here. It's also, so they give you how to use this. Basically, this model was evaluated on WikiNER, WikiANN, and NCC, and it achieves, as you can see, quite impressive results, right? So that's and yeah, so when training it, we used the Bengali Wikipedia dump and the Bengali portion of the Oscar dataset. Oscar is a bunch of Indic languages, so including Bengali, actually a bunch of languages, including Esperanto as well. So in any case, I also wrote a blog post which contains some more details. This is what Arto was talking about. Mainly for me, it was like, I had never seen my language represented in computers, right? So I was actually quite kicked with the idea of how it was represented in Unicode for some, but the blog post also contains paper references and the charts. So so the training process lasted for about a week, and there were between 20 to 50 simultaneous users, from all over the world. And over the course of the week, the loss went down from around 11 to under 2, right? So the charts are all here. Let me share this. And also the precision recall curves for the, let me see here. Where is this chart? Stop share. Maybe I'll stop share. Okay. So the blog post is here, and it contains, additional information that I didn't cover here. I think that's pretty much all that I had. Yeah. So basically, that's what I had for the Albert training.
So the tasks were the usual pre-training tasks.
Yes, tasks were basically mass language modeling and sentence, sentence pair, the SOP, whatever that is, I forget. Basically it says whether sentences are, they belong together, they come one after the other, right? So they use both the tasks for Albert. But Albert is slightly different from BERT, as far as I understand, is that the layer weights are tied for some reason. I don't know exactly how that works. But that's what I read in what is the difference between BERT and Albert. So their weights are tied apparently.
This is nice. How much time did you invest with respect to the training? I
Um,
mean,
so I think if you go on the model card, I'm on the leaderboard. Yeah. So I think number 12 on the leaderboard. So I invested around. So there were 2 training runs. One was like a warm up, kind of getting everybody to figure out how to get everything running. And so over a period of 2 weeks, I think I ran my full quota of Kaggle over 2 weeks. Actually, I took 3 weeks of Kaggle, so 30 hours of each. Take away the first, so maybe about 40 to 60 hours of Kaggle and similar amounts of Colab. So that's what I contributed, but I am actually number 12, and the guys ahead of me actually contributed much more. So yeah, so it's actually enormous amounts of training time, but free GPU resources. So you don't have to pay for GPU. Well, somebody has to pay, but the training group doesn't have to pay for GPU. And it was over a period of 2 weeks. So, and the number of people varied. So if you go to my blog post, there is there is a chart where it shows how so in the first block, the second chart, right? So the max we had were like 50, 55 simultaneous users. And the min we had, so the min we had was actually less than 20, but overall it'll be 20, 25 users throughout.
nice. Between Albert uses some parameter reduction techniques along with a couple of uh, features that are suited to distributional environments with respect to I was going through the paper last week, yeah, and I found that the parameters with the BERT ones, the BERT base had 108, and the Albert had 12 million
Yes.
parameters.
Mm-hmm.
Yeah.
Yeah.
So yeah, with respect to the same hidden layers it had. So and that other than that, I think so they had the lamp optimizer that they used. So
Yes, that's true. Yeah, lamp optimizer. Yeah.
Yeah. Cool. Thanks.
Yes, sure. I think there are in the blog post, there is also some GitHub repos where we were given like a notebook to run. Basically, we had to put in our own Hugging Face IDs so that they could track us. But apart from that, it was mostly code that they gave us. So we were just running things. We were not actually writing anything. But I pointed the GitHub. There is a GitHub link in the blog post where you can see the notebooks. So that gives you some idea of what was more like what I described. That's in code. So yeah.
Nice. So, any particular reason for going with Albert instead of? I think so nowadays there are specific character level uh, uh, transformers like for in Japanese text. So I was thinking those are particularly specialized for this. I am currently light with the details right now, but. Uh,
Yeah, I'm not sure why, Albert, that decision was made before I joined.
Okay.
But one thing I found, since you mentioned Japanese text, CJK is a slightly different ballgame than Indic. So CJK is like glyphs, right? Each glyph has, means a lot of things. But Indic languages seem to be more along the lines of English, where you have, it's slightly more complex than English. So English, you have basically characters strung together to form words, right? Here you have a combination of consonants and vowels, right? So, e, right? These are all the vowels, and the ka, kha, ga, ga are the consonants. And you basically, combine them to form words like ku, ka, ki, right? So this sort of thing, right? So, and that becomes like a, pseudo character, right? Once you add them up. But if you actually unstring them, if you say C for C in the string, right? You basically get back the original things. So, which was surprising to me. I actually mentioned that in the blog. It's more like, you learn how your language is represented in a computer. So that was a big thing for me, right? So, yeah.
Nice. Thanks.
Yeah, sure.
Thanks, Sujit, for sharing. It was really interesting.
Sure. Absolutely.
Okay, if we don't have any questions or anything to add, we'll end the meeting. Thanks everyone for joining. Thank you.
Thank
Thanks,
you.
Sujit.
Bye.
Thank you.
Thank
Thanks,
you.
guys.
Bye.
Take care.
Bye.